Hey, good evening, everybody. 6 o'clock, let's get started. I hope you are ready and already went through our lecture material for tonight. Is there any questions or anything? Let me also check the discussion if there is anything, or you can ask me. Oh, nothing is on the module 1 QA, seems like. Okay, since you are here, why don't I start with a poll? Let me see. Okay, let's take a couple of seconds to do this simple poll, okay? This is about the class preparedness poll. It's asking first question, have you watched lecture video, read lecture note for today's topic? Another is that have you noted your queries in the corresponding discussion page? Okay. 19 of 23, 20 of 23. Okay, all of you have participated. Let's end the polling and share the result. Let's see. Have you watched the lecture video, read lecture notes for today's topic? All of them about 57%. This is good. Thank you very much. None of them, there is one, please follow through. And some of them is about 39%, rest of 9 people. Please make sure you actually go through all the materials before coming to the class. That will make the class discussion more effective. And you will pick up more from the live session than if you don't read it upfront before coming to the class. Anyway, tonight our topic was we are kind of introduced to the computer, and we know all computing systems and computer, etc. And you can ask me question at any time. But let me do one thing. Let me give you a different perspective of computing system and try to explain really how computer works. Means given a small program or high level program, how computer execute that program really in background, right? So that would be some interesting thought, and it will have many other informations. This discussion will have many other information, I guess, and that will give you at least the overall bird's eye view of the entire course, these semesters, like how a system works and what are the different components, what is their overall participation in computing process. So let's get started. Let me share my screen first. Share. Okay. And then, all right. Now, what I want to introduce you to memory, right? I hope like you have already heard this term memory in conjunction with your computing system, right? Your laptop or desktop is, let's say, has 1 gigabyte of memory or 512 megabyte of RAM. It has, let's say, half terabyte of hard disk, that kind of thing. It's a storage element. And especially in memory, when we are talking of here in this context, is that RAM we are talking of, like your primary memory, what you call it in general term. When you, let's say you go to Amazon, buy a laptop, what you look for? You look for the processor, what the processor speed is, and how much memory it has, how much RAM it has, right? So that's the memory we are talking of. And in a very simplistic sense, that memory, RAM, is nothing but an indexed storage, just like array. I hope everybody has used array in your programming part, like arrays type of variable, and you access it, the values with using the index, right? So you can think memory as an index storage, just like the array, and it stores values. It stores values, okay? It stores values there. Even your strings or other text representation, all are represented using values. Like computer doesn't know anything outside numbers. So there is nothing really from computer perspective, there is nothing other than numbers, okay? So we store values in this indexed storage. Let's say we have many such storage in the memory starting from the index 0, let's say all the way to 99,999. Okay, so till that index. It's not an absolute range, I'm just giving you an example. Now we can access the values in this storage by its index, just like array, by its index. Okay, give me the value of at index 5 or 7 or 9,099, something like that we can do with this. Okay, so this is an array storage. And let's say there is an actor associated with this. Like let's look at this whole discussion from the actor action point of view. Let's say there is an actor called MMU. Okay, MMU stands for Memory Management Unit. What it does is basically operates on this indexed storage as request comes in. And this whole thing, we call it a memory, okay? Memory management unit with that storage space, this index storage space is called a memory. And in terms of memory, this index is called address. So whenever we say memory address this, memory address that, we really means the index value, at which index we are referring to, okay? So address and index is kind of synonym in this context. And we'll use memory address much more in this course than index, okay? Memory address is much more terms used frequently in the hardware world. So that's why we'll be sticking to the term address instead of index, okay? Now, what this does? It basically does something like this. Someone can just instruct it something like this: write the value 5 at write the value 5 at index or address 3. Okay. So this instruction, if it is sent to the MMU picks it up and simply write that value into that index or that address, that storage of at that address. We can do similarly, like let's say write 13 at 1 at address 1. So it will write it there. It will store that value at that index. Then we can say something like read at 1. So read the value from address 1. So what it will do at this point, it will basically return back 13 from the memory, right? So far so good. Any question? Okay, now let me introduce another actor in the computing system. It's called ALU. Okay, it's called ALU, Arithmetic Logic Unit. Its function is very simple. What it does, you ask it some mathematical outcome, let's say 3 plus 5, what is that? It will give you back the answer, 8, for example. Okay. So another actor, ALU, very important, it's Arithmetic Logic Unit. Another system, or I would say subsystem, is called a register file or register file unit, RFU. This thing is basically a memory, okay? Basically a memory It's an index storage. The difference between the memory, the RAM we talk of, and the register file is that, first of all, register file is really very high speed device. It's operate very higher speed compared to the memory. It's very fast. Register file storage retrieval is very fast. And on the other hand, number of storage in the register file is limited. For example, here I have shown you like 32 storage in the register file. It's a 32 register system. Sometimes a computing system can have like 128 register, 256 register, something like that, but really not as huge as a memory or RAM available in a computing system. A computing system can have gigabyte range of RAM, like 16 gigabyte, 32 gigabyte of RAM. Even that high-end system is possible, but number of register is always limited. It's 32, 64, 128, maybe 256, maybe 512. I haven't heard anything beyond that, but maybe some new are coming up with more registers in it. But its basic point, its number is limited, but it is super fast storage element. But operation point of view, it is no difference than a memory. It's basically you are writing into the registers, into their storage, and retrieve back with a read. There is a little bit twist there, a little bit difference in the reading operation. I'll explain you it in very time when it is needed. But right now, just take this register file RFU unit is practically same as a memory, but it is faster, but limited in size. Question? Anything? So far we are good? All right. Now let me introduce the big boss, the controller. Okay. This is the gang leader. Okay. This is the mastermind. This is, you can say it's an in a musical world, this is the conductor, right? In the music symphony, this is the one who synchronizes music between different player, right? And this is the most one vital important role it carries in the computation world. It's called a controller. And together, controller, RFU, ALU, these three together makes the processor. So when you are talking about Intel Pentium processor or ARM processor or any other system, practically they have this basic actor there, okay? Register files, controller, ALU inside them. So that's the processor. Now, let us take a very simple example of a very high level program, okay? Like this. Let's say there is a variable integer a10, integer b20, integer c equal to a plus b. How computer execute it? Like, this is a very simple, like 3-liner code. And what computer does, how it performs, okay? That's the mystery we are trying to discuss here from now onwards. First of all, each of these high-level variables are assigned with some memory address. It is done by compiler. So I hope you have heard about the tool compiler. Sometimes you probably used in some class, like especially if you program with C, C++, that area, you need to use a compiler tool to compile your program. Java world, it is more like an interpreter language. Maybe I don't have much exposure to Java, so probably you know more than me about the Java language program. But as far as theoretically, you know, it is interpreter-based language. There is no compiler involved in between, or in real sense compiler, but you can probably comment better than me on that. But however, in both systems, whether it is Java, Python, any high-level language you can pick up, variables are always associated with a memory address. Let's say some association is done like this. Let's say A, we assign the address 0 in the memory. So whenever we refer to variable A, we mean the content of the 0 index, address 0 in the memory. Similarly, B is assigned with an address 1 and C is assigned with address 2. All right. Now, next step, this high-level program is broken down into very basic, smaller instruction. It is done by compiler, okay, under the hood, or interpreter like JavaScript or Python. If you run, it's done by the interpreter. So this compiler, what it does, it takes this program, high-level program, and break it down into lower-level program. This lower-level program, we call it an assembly program or programming assembly language that compiler already automatically convert high-level program to the assembly level program. Now, you see this is like some very basic step, write 10 at the address 0, write 20 at address 1, read at the address 0 and store it at the register file 0, read address at 1, store it at register file 1, then read the register file 0 and register file 1, add them together and place the result in register file 2. And next one is read at the register file 2 and store it at address 2. So it breaks down into these basic steps. Now, then another tools comes into the picture, which is called assembler. We'll be studying in this class more about this assembling and assembling process, etc. But at the end of the day, this assembler picks up this simple step that compiler generated, that assembly program. It takes those and convert into the machine code. Machine codes are nothing but numbers, values. Okay, machine code is nothing but numbers. So it changes to that. Later we'll actually review how the machine code is generated from a given assembly instruction and so on and so forth. We'll review that, but for time being, just assume that assembler can do it, change that assembly program into machine code of that system, of that processor, that the processor understand. Now, from this point, what we need to do is to first, when we start a program, let's say you start executing a program, what happens? The machine code corresponding to that program gets loaded into the memory. Okay, so it goes into the memory first, and then processors start executing them from the beginning. Okay, so let's do that. So before going to that, let me know if you have any question till this point. All right, now let's load it. So we already assembled it. We have this machine code. Let's load it into the memory. Okay, let's load it into memory. So, okay, I just expanded a little bit to magnify that memory area and load those machine code, let's say from address 3, because address 0, 1, 2 already assigned for those variables. So I just started from address 3. By the way, in the real life, it is not done this simple, and more we'll be looking at later in the class where this program is loaded and so on and so forth. And many more details will come up in your operating system class, which is very related to this course. Okay, so just we are taking a very simplistic view here. Like we have machine code, we load it in the memory from address 3, and then let's see what happens. Now, what happens, to explain it, I need to introduce you another component inside the processor, which is a very small, tiny component, which is called a PC or program counter. Okay, PC or program counter. This is like an you can say this is a scratch pad for the controller to see where from to get the next instruction of the program. Okay, so it is when you start a program, your program counter is set to the address of the beginning of the program. So in this case, it will set to 3. Okay, it will set to 3 because your start of the program is from the address 3. So program counter set to 3. Now controller knows from where it needs to pick up the next instruction. So controller goes into these cycles. Okay, one is called instruction fetch. So at this point, controller issue instructions to the memory that, hey, read at the address 3. That 3 is coming from this program counter, simply. So what memory will do, it will simply return the value stored in that location 3, right, which is 2654778. So it will return that. Now, after this, processor goes or controller goes into the next phase, which is called instruction decode. Okay, instruction decode means at this point, it looks at the value, parts it, break it up into different components, and try to see what this instruction is intending to do. Okay, so after parsing and instruction decoding, it realized that, hey, it wants me to write the value 10 at the address 0 of the memory. So what it will do, it will basically send that instruction to the memory, hey, write 10 at the address 0. And what the memory do? It will write that value into the memory. So that gives you the A equals 10 execution. See, the A equal to 10, A is associated with that address 0. Now that address is loaded with a value. So that is initialization of that variable is. And also note your program counter changed to 4. This is like at the end of the execution of that instruction, the program counter changed to 4 to point to the next instruction, which is like machine code is 123481. Some arbitrary number I have as an example put there. Don't try to overanalyze these values. Okay, it's just a sample number. So what it will do now? Next, again, go to the instruction fetch. So it will tell controller tell the memory that, hey, go and read from from address 4. And what memory will do? It will return that machine code. Then instruction decode comes in that phase, and then controller sees, okay, well, I want to write 20 at address 1, so it will issue that to the memory, write 20 at address 1, and memory will happily write it 20, and program counter jumps to 5 now, like pointing to the next instruction. Now you see, like we are done with this next high-level instruction, which is B equals 20. Initialize that variable with 20 means corresponding address is loaded with that value. Okay. Now goes to the next instruction. Okay, it is 5. Now next instruction fetch, read at 5. It will return that instruction machine code to it. Instruction decode. Now it will go to the instruction decode and see that, well, I need to read from address 0 and store that in the register file 0. So at that point, what controller will do is, first of all, send an instruction to the memory, read at 0. Memory will return the value 10, right? 0 address, we have the value 10. So it will return 10. And now controller will instruct the register file unit that, hey, write 10 at 0. So it will store, register file is stored, the value is 10 into the register 0, and program counter is updated to the next instruction, which is address at 6. Program counter is set to the 6. So this same thing happens, instruction fetch, read at 6, Memory returns the corresponding machine code. Controller decodes, instruction decode phase, controller decode that and say, hey, I need to read from address 1, store it to register file 1. So what it will do the similar thing like the previous step. It will issue an instruction to the memory, read from address 1, memory returns that value 20. It will ask register file unit to write that value 20 into that register 1. So this 20 is stored now in the register file, register number 1 there. So far so good. Any question? All right. Now let's see. Now next, instruction fetch, read from address 7, memory returns it, the corresponding machine code. Now instruction decode fetch, controller decode that instruction and sees that, now I need to read back from register 0 and register 1, add them up and store it in register 2. So what shall we do? So it takes this following course of action. It issues read at 0 and 1. Now, remember I told you register file is little bit functionally a little bit different than the memory. Here is one important difference. Controller can issue a parallel read to the register file unit. It can ask register file to read two register together at the same time and give it back both the value together at the same time. Memory unit cannot do that. Memory is always one address at a time. One address, you give one address, you get the value one address. You cannot issue two addresses in parallel. But for the register file, it is possible that you can request to read at the same time. So it is controller using that feature to retrieve both the values 10 and 20 together at one time, one single point. And it issues simply read at address 0 and 1. And register file happily returns these two values, 10, 20. And then controller issues this instruction, hey, what is to the ALU? Asking ALU, hey, what is the 10 plus 20 result is? ALU returns back the value 30. And then controller issues register file with the instruction write 30 at register 2. So at this end of this instruction, 30 is written at register 2. And program counter bumps to the next instruction address, which is 8 in this case. Now it goes like this, again instruction fetch from 8. Memory returns that value to the processor, to the controller. Instruction decode fetch, controller thinks and decode this whole instruction and say that, hey, now I need to read from RF2 and store it at address 2. So what it will do, it will simply issue read at 2 for the register file. Register file returns this value 30. Then it asks the memory to write 30 at 2. And memory writes it there, 30. Now you see at the end of this instruction, it's basically complete your high-level instruction C equal to A plus B, isn't it? So we expect the C values of the C to be 30. That means corresponding address to store 30, that address 2, that exactly happens here, right? We are storing value 30 at address 2, and that's the end of this simple program. Now see, like we took probably 10-15 minutes to explain it, what is going on inside the processor with this simple like 3-liner program, high-level program. Now, believe me or not, this is exactly what happens in every processor, similar things. It fetches the instruction, decode it, and take some action based on that decoding value involving those actors, register file, memory, ALU. Question so far? All right. Now I told about the assembly program. I just showed you here a little bit like simplified step that compiler do. In fact, if I think to write an assembly program corresponding to that, this machine code, it would look like something like this. Like these are called instruction in the assembly, some add-I, store word, etc., etc. We'll all study them, how to write an assembly program. And we'll target a processor called MIPS processor. We picked up that for the class because it is very easy to pick up that assembly language, very simple assembly language. We just pick up the concept, and in this class, we'll use these assembly language programming to explore hardware characteristics and understand the hardware activities. Okay, so mainly I want to emphasize on this point. This class is not for just learning assembly language or become a master of assembly language. It is not a language class. It is not a programming class. We learn assembly language as a tool, okay, to explore underlying hardware and understand the hardware behavior, how things are done inside the hardware. That's our target for this course. Not that our real target is to learn assembly language and become master of the assembly language. All right, question. No? Okay, let's take 5-minute break, then we'll be back. Hey, is it already 5 minutes? I lost my track of my time. Can someone confirm it is? Okay, Alex said it's yes, it's already 5 minutes. Oh, by the way, I forgot to start a record on the Zoom. Let me start that. Okay, yeah, I'm just starting the recording on the Zoom. That means the first part will be missing from the recording on the Zoom. But good news is that since I stream it to the YouTube channel, at least that will have the recording. So you probably may want to refer to that one instead. But anyway, where were we? We were looking for how the processor computing system works in a nutshell. And let's get back to that one and give you another interesting perspective. Let's take this slide as an example. Okay. Share the screen. Okay. All right. Now you see that that the controller is issuing an instruction to another actor, like either memory, register file, or ALU. In this example, it is sending an instruction to the ALU that, hey, add these two values and give me the result back. And then ALU is giving back the result. The big question is when ALU gives back the result, at what time? Let's say right now, controller issues an instruction to the ALU. When can controller expect it back, expect the result back? And that concept is really, really important because you see, this is like, though I have drawn it as a human figurine, but they are not human like us. They cannot like see really face to face. I ask you, for example, what is 10 plus 20? You speak up and say 30. I know, I receive your answer, that your voice, and know you are done. It is all electronic world, right? They are connected via electrical, I would say electrical wire, you can say, electrical wires. They are connected via electrical wires. And then they talk with each other with respect to electrical signals between them. And in a digital world like computing system, you can say if there is no current or no voltage on an electrical wire, it's assumed to be of value 0, like binary value 0. And if it is turned on, or it has a current, or it has a voltage, that wire is assumed to have a Boolean value of 1. So Boolean value 0, Boolean value 1, or binary value 0, binary value 1. This is the convention of the electronic system, or digital electronic system, I should say. That presence of voltage represents a binary or Boolean value 1, and absence of voltage represent the binary value or Boolean value 0. Now you see, that means there is no such state like which says that, hey, I'm still computing, I'm not done. 0 is a valid answer. If something is not on a signal, it's 0. It may be a valid answer. Who knows, right? 0 plus 0 is 0, for example. So now point become that controller is receiving some sort of like digital signal from the ALU, but itself it does not tell that if it is a valid answer or not, if ALU is done with computation or not, and present and sent that value over that electrical wire. So then how controller knows? So there comes this whole concept of timing, that it is an pre-assigned assumption between the controller and rest of the actor that says that if controller issues an instruction to the other actor like ALU or RFU, etc., they will generate a result at the end of certain time period. Okay, so means that at this moment, if if controller issues an instruction of addition of two values to the ALU, controller assumes that if it probe on that electrical line after, let's say, 10 nanosecond, the result will be there. Okay, so this is the concept of the time now comes into the picture here. So controller assumes that there is a fixed time of interval after which it assumes whatever instruction it sent to the other actors, it will be done by that time. So that is very critical and important concept of timing. Okay, and how much is that interval? It is really low. It is not even microsecond range. It is nanosecond. It can be nanosecond range, which is like 1 nanosecond is 10 to the power minus 9 second. So this is that small. So maybe 1 nanosecond, maybe 10 nanosecond. So it is a pre-assumed timing information that all these components agreed to. So controller agrees that after issuing an instruction, I expect the answer to be ready by, let's say, 10 nanosecond. All the other actors know when it gets an instruction, it should produce result by that time, no later than that time interval. Okay, so that's the concept of the timing. Question so far in that concept? All right, now let me explain a little bit on the clock. Since what we have agreed so far, there should be a concept of timing between these different components. This timing, this timekeeper is, or time representation is something called a clock device, which I haven't shown in the computing system, but it is actually in every modern computer system, there is something called a clock. And whenever you talk about a processor has 1.2 gigahertz frequency, 1 gigahertz frequency, something like that, all you are talking about this clock, how much is the time period of that clock is, that all you are talking about. That means less time period means you have high speed of operation. More time period means you have lower speed of operation. And frequency and time is inversely proportional. If you took physics class, it's basically classical physics definition. Frequency equal to 1 by time period. Okay, or time period equals 1 by frequency. It's that definition. So if you go with the higher frequency, means you are actually going with the higher clock speed, means you are narrowing down the time period of the clock. Saying that, let me explain what is the time period and what is this all clock device, which gives the time reference to all these components in the computing system. So all these components, you take RFU, you take ALU, you take MMU, you take controller, all of them are connected with this clock signal. Okay, this is the common signal goes to every other component, which gives a timing sense to each of this component, and they can agree that, hey, if I have been presented with an instruction at this time point, I will be finished by this time point. Okay, so that's the reference, time reference that is provided by the clock system. Let me explain a little bit on that too before we stop for today. And by the way, next lecture will come up with for more on this clock system and all these studies. Let me explain that. So, where is my whiteboard? Okay, here it is. Share. Okay, now a clock system is an electronic system. It resides on the computer, which is like, let's say we draw some black box. Okay, let's make it a clock. So what it does, it electrically create pulses of voltage on the timeline. Okay, so to capture that, we need to learn about little bit about the concept of timing diagram. What the timing diagram is let's say clock is giving out an electrical signal. This is, let's say this is an electric wire. So timing diagram shows that what its logic value with respect to timing, with respect to time. Okay, so this is my x-axis goes to the time as a time, and let's say this time is divided into smaller segment, like 1 nanosecond, 2 nanosecond. By the way, 1 nanosecond equals to 10 to the power minus 9 second. Three nanosecond, 4 nanosecond, and so on and so forth. Right? So it is time scale is divided into this small chunk. And let's say I have let me just draw some reference line there. Okay. Now, if a signal, a digital signal like clock, like this clock, the electrical line, if you look at and probe at, if it has no voltage, it represents with a logic 0. Okay, so let's say during the time point between 1 nanosecond and 2 nanosecond from the start, its value is 0. Then it goes up to value of logic 1, and then it goes down again to value 0, then goes up to value 1, value 0, value 1, and so on and so forth. So the clock system actually gives a digital signal of continuous stream of logic 0 and logic 1, which is like presence of voltage, absence of voltage. Not only that, it's constrained that this is an uniformly spaced along the timeline. Okay, so for 1 nanosecond it is 0, next nanosecond it is 1, another next nanosecond it is 0, next it is 1, and it is continuous up and down in the logic level. Whereas other arbitrary signals, maybe let's say another logic value, I don't know, let's give it a name, a digital signal called A. It can have, depending on what logic function we are evaluating with respect to that, it can go up sometime and stay down, and then go up, then stay down for long, then up. It really depends on the logical function we are implementing on that specific digital signal. But clock itself is guaranteed to give a continuous stream of 0 and 1 with a specific time interval. In this case, what is the time interval? It is the 1 high edge, logic 1 edge to another logic 1 edge. So every 2 nanosecond, it will repeats its value. Okay, every 2 nanosecond. So within 2 nanosecond, it goes to the same value every 2 nanosecond. If you look at the 0 also, from 1 0 to another, the difference, time difference is 2 nanosecond. So that means what we can say in this diagram, your time period is 2 nanosecond. That means we can compute the frequency as 1 by t, which is 1 by 2 nanosecond, which is like 1 by 2 into 10 to the power minus 10 second, which is 0.5 into 10 to the power 9 hertz. 1 by second is hertz from the physics definition, which is like 0.5, 10 to the power 9 is gig, it is gigahertz. Okay, so 2 nanosecond frequency, 2 nanosecond time period means a clock of half gigahertz, 0.5 gigahertz. Question so far? Okay, now one more thing, since we are here in this discussion, this logic value change relation between some digital signal like clock or A with respect to the time is called a timing diagram. This is a timing diagram. Okay, and if it is a single logic value, like the clock or A, you can represent with just one single line. However, if it is a bunch of logic together, let's say something called data, some logic signal, which is like, let's say it's an array of 32 elements. Okay, together the bunch, we call, in a hardware world, we call it a bus, like a data bus or data unit. So they kind of represent information together. That's what they are called. They are bunched together, and they represented as a trapezoid. Let's say let's say they have a value. So they basically represented like an segment. It's not a line. It's basically a rectangle. And let's say at this point they change the value. So this is being represented as this. So means it was having one value. Now it is having another value. And let's say at this point it again changed. And sometimes you will see that sometimes we represent the values of the cluster of digital signal or bunch of digital signal or bus signal as a dotted line. This means really there is a value, but I don't care. Don't care about this value. This value. Don't care about this value. So dotted line means this. If there is a trapezoid lines like this, it means there is some value of interest. It represents some value of interest. Okay. What it represent, what value represent, will be learning it down the course, definitely, but it is more like an introduction to the timing diagram. Just assume that bunch of signals, digital signal, bunch of bits can represent some real numeric values together. Question? Okay, now let us see if we don't have any other question.
Professor?
Yes.
Yes, I do have a question. Could you go back to the previous slide?
Okay. You mean to the diagram?
Yes, to the diagram, please.
Okay, share screen. Yes, tell me.
Just to be each hexagon in the green one at the bottom, each hexagon represents yes, that one. Yeah, each one of those represent a data block being constant throughout the time period, right?
Yes, data being constant at constant value at that time period. This between this time period, in this time period, yes.
All right, and the core and the instances where the corners meet is the instance when the data block changed value.
Right, exactly. So it means that at this specific point, it changed the data, switched the data. So
All
at this,
right. Okay, cool. Thank you.
all right.
Wait. One more thing. I
Yeah,
just realized.
sure.
When you have data that's only 1 bit long,
Mhm.
you can have data that's only 1 bit long if we determine it to be data, right? Do you still represent that as the hexagons, or do you use the electric
This is, yeah,
wire
if it
thing?
is the 1 bit data, I would say just use that logical line like 0 or 1 to represent them.
Okay. All right. So 1 bit data we can represent with the logic and I mean, yeah, the 0 and 1 logical thing.
Right.
But yeah, but then using the hexagon
Group of data.
representation just says there is data that we care about. It just doesn't represent what the data is.
Right, right. Now you can choose to draw them separately, like data 0, data 1, data 2. This will be too much to draw in the timeline. That's
I
why
see.
people go with a bunching them together, basically.
Okay.
Remember, individually they're single bit and they can be represented as high and low individually.
Oh, okay. I see. They do represent a bunch of different lines together.
Right. They do represent
Okay.
bunch.
No,
Yes.
they don't refer to some high level data structure like an array or an array list or something like that.
It depends on how you interpret that group of bits, group of
I
values.
see.
It all depends on our interpretation.
Okay. All right. Thank you, Professor. That clears it.
Okay, now let's quickly look at what's coming up for us. Next lecture. Let me. Okay, let's see. Share screen. Okay, now next is coming up next day in lecture 2, right? So if you go to the module 1, lecture 2, and this one has quite a lot, like it's at 6 part of the different videos. And let me describe what this contains. We will be actually being introduced with this different component. The actor we just introduced, ALU, clock system, I just talked a little bit about that. We'll be studying more on in this lecture. And then memory system model and register file model, both the actor I have introduced you today, and control unit model. Okay. And again, this is notes from my experience, so no reference to your textbook or anything. Just go through this note, and if you have any questions, concern, just put it on the Q&A discussion page or just ask me in the class for them. So ALU will be approaching it a little bit from the API side, like we all used software API in our software programming. I just try to draw some analogy between the software APIs and what the real hardware schematic model interface diagram means in terms of API, so that it kind of resonate with your programming world that you are used to so far. Then we'll move to the clock system model, try to explain why it is needed, the clock system, etc. Then it goes to define some of the characteristics of the clock system model, time period, duty cycle, etc. that you need to know and should be able to compute them if some problems comes in. Then we talk about the memory system model, again, approach through the API way to understand what really does in the computing system. And then with respect to the timing diagram, we try to explain how this functionality works, like what it needs. And especially there will be a very interesting observation. You will see that there is an sequence of the instruction read and write, and for many memory systems it is not possible to issue a back-to-back read and write operation. Like if you read something in the very next clock cycle, you cannot actually issue a write to the memory system. It explains why it is like that. So that's very interesting phenomena that you want to understand thoroughly. Many problems can be formulated with respect to that behavior. So please make sure you pay extra special attention to that fact. And then we'll move to the register file model. So here what I try to approach it to more like we start like a memory model. As I said, like register file by behavior is not very much different than the memory. So we start from a memory model and then modify it into the register file with, like, let's say first splitting out the data bus between input data, output data, separate them out, and then introduce like parallel data read capability into it. So that the approach will be taking to understand the register file model. So we'll start with the concept of the memory and morph it into the register file. So that's what we're trying to do here. And then we talk about the control system model, what it does, what it is role, which I showed you to today's discussion. What it does is basically that synchronization operation between different components in the computing system. And through that, it ultimately achieves the goal of executing a high-level program that you write on a system. Okay, so please review this lecture. I hope I'll get more questions on the Q&A and more questions in the next class from you so that we will have a more effective discussion. Remember, like if you don't have question, that means either two of the thing. Either you have understood everything or you haven't understood nothing, like you haven't understood at all the whole thing. So only these two conditions, you won't have any question. If you understand, like, and read through, I believe you will have many unanswered questions there in this chapter. So please make sure you read through, try to understand, and make sure in the next class, clear up your concept. This is very much fundamental. Question? All right, then let's stop tonight and see you on Thursday.